Hello and a very good day, everyone. Let me start my presentation today with a word from James Dyson, the founder of the Dyson Company. Manufacturing is more than just putting parts together, it's coming up with ideas, testing principles, and perfecting the engineering as well as final assembly. And I believe that we are here today are because of that. Ladies and gentlemen, I am Aizati from University Technology Malaysia. I'm here today to share with you on the analysis of resistant spot welding of various steel using numerical computation. I believe that everyone here are familiarized with the spot welding process, right? To begin, resistant spot welding process have been utilized in a variety of industries for over a century. Over time, the method has advanced into a standard and prevalent strategy of combining thin metals such as steel sheet. The spot weld process is employed not just in the automobile industry, but also in aerospace and packaging. Spot welding is most typically used to join parts that are less than 3 mm thick. However, if the more thickness might be less effective. The spot weld technique was divided into 3 parts to provide the best results, which are squeezing, welding, and cooling. Each stage will require the definition of a few additional parameters such as squeeze time and electrode time during the squeeze phase, weld current and weld time during the welding phase, and electrode hold time during the cooling phase. Electrical and thermal conductivity, on the other hand, is a crucial consideration in spot welding. A molten weld nugget occurs in the workpieces as a result of the contact resistance and joule heating. The physical action of current traveling through an electrical conductor producing thermal energy is known as the joule heating. Thermal and electrical contact conductivity are critical in determining the rate of heat generation and nugget formation. As a result, when the temperature rises, so will the bulk resistance. Then, when sufficient heat is created on the workpiece in the resistant spot welding, the weld nugget will absolutely form. The finite element method was utilized to delve deeper into the resistant spot welding process. This is due to the fact that this strategy is not only cost-effective but also efficient in terms of time. In comparison to the experiment, the results obtained are more detailed. This procedure can be repeated numerous times without consuming any hardware. The aim of this research is to use the software MSc-Mark method to simulate or analyze the finite elements for the resistant spot welding process of 3 different materials, which are SS316, DP600, and S235, and to use them as a reference, standard, or guideline in order to improve the accurateness of the finite element simulation of the resistant spot welding in the future. The process modeling of resistant spot welding in MSc-Mark method is fairly hard due to the large number of parameters that must be defined. The increasing need for resistant spot welding techniques for combining different materials has coincided with an increase in the number of materials made available in the industries. The most difficult problem, however, is determining and specifying the proper limits for each material. Furthermore, exposing all of the materials to a trial and error resistant spot welding technique each time is likely to be exceedingly time-consuming and waste significant amounts of resources. The spot welding process simulated in MSc-Mark method generally can be simplified into 10 sections as shown in the figure. The FEA simulation of spot welding process in MSc-Mark can be divided into 3 phases, which are pre-processing, solving, and post-processing. As can be seen on the screen, the pre-processing stages, which is geometric and mesh, can either be imported or directly be drawn and meshed in the MSc-Mark itself. Among the important parameters that need to be defined are including its materials, contact bodies and interaction, initial and boundary condition, and the load cases before can be run to get the results. Next, it is critical to verify the length unit before attempting to sketch the geometry. The unit of measurement in this simulation is in millimeters. The resistant spot welding process component employed in this simulation comprises of 2 pieces of 100 mm long, 45 mm wide, and 1 mm thick plates. The 2 copper electrodes employed in this simulation are in the shape of truncated cone. This table, as viewed on the screen, displays the values used for each parameter set for this simulation. Except for the weld current, the three materials have the same electrode force, squeeze time, weld time, and hold time. The weld current varies across the three materials, with S235 requiring 15 kA and DP600 and SS316 requiring 13 kA. Next, this is the chemical composition for each of materials used in this study. When creating the simulation, there are a number of properties that must be assigned. Because the MSc Mark software lacked a database of material properties, everything had to be manually assigned. These 4 properties are among the ones that have been assigned. The graph depicts various colors of lines which indicate various types of materials. As can be seen, different materials have varying values of characteristics. These qualities are critical because if they are not determined correctly, they will have an impact on the final result. For example, if we did not apply thermal conductivity when developing the model, there would most likely be nothing between the body and the plate because thermal conductivity is one of the main reasons of resistant spot welding. If there is no thermal present, heating definitely will not occur, right? Subroutine glue deactivation is applied to all nodes except at nodes that reach predefined temperature, which defined at the spot welded joint. In simulation, the job process is the final phase of each simulation that has been created. Before submitting the job simulation, an additional step of assigning user subroutine was required to specify the fusion region of spot welded at the end of the simulation process, with the goal of permanently gluing the top and bottom sheet plates. In the user subroutine, the temperature of the subroutine has been set to 800 degrees Celsius. If the node reaches 800 degrees Celsius during the spot welding operation, the user subroutine will assist in switching the contact interaction between plate and plate from contacting to a permanent adhesive. Both metal sheets will be attached as a result. Next, we are gonna see the simulation on the result of how the weld nugget created on the spot welding process. This simulation showed the spot welding stage, which consists of 20 increments altogether. Following the completion of the simulation, the temperature study findings can be shown on the model. During resistant spot welding, a link between the surface temperature of a spot weld and the greatest temperature at the nugget center can be created. After that, the relationship can be calculated. It indicates that the weld bore the highest temperature in the weld center. The temperature values are shown by the scale gradient on the figure's left side. The lowest temperature is represented by the color gradient at the bottom of the scale, while the maximum temperature is represented by the color gradient at the top of the scale. Theoretical considerations suggest that there should not be a considerable difference between the size of the weld nugget and the size of the electrode tips, as shown in the image. Nonetheless, the formation of the weld nugget cannot be visible in this finite element research, but based on the temperature, we can deduce that nugget formation is taking place. As an example, in the screen, it is expected that weld nugget formation will commence when the temperature hits 1000 degrees Celsius or more. As a result, the gray area had a temperature of 1000 degrees Celsius, indicating that the weld nugget had been created perfectly. Meanwhile, there are several more types of current that can be used, such as point current, phase current, edge current, and volume current, which might be employed for the study. When utilized, the entire current statement will show a different analysis. The link between the current value, temperature, and the point current can be shown on the basis of the table presented on the screen. The point current in this study is one of the factors that can be modified to obtain the desired temperature. The point current is directly connected to the current set for parameter and the number of nodes. A point current is a value that indicates each node's current. To obtain the overall current, the point current must be multiplied by the total number of nodes. For all the materials used, which are S235, DP600, and SS316, the total number of nodes for the electrode is 117 nodes. Next, the weld nugget diameter is roughly 3 mm when the peak temperature of 1400 degrees C is attained with a current of 15 kA and a point current of 130 ampere for the S235 steel. For DP600 and SS316, however, a point current of 13 Ka and 111 ampere is used to attain temperatures of 1360 degrees Celsius and 1557 degrees Celsius respectively. One of the main reasons for the temperature variances is related to the chemical composition of each of the component. For example, the amount of ferrum present in S235 is substantially higher than in DP600 and SS316, making it more difficult to melt. Another reason is that the current usage values differ from one another. However, the weld nugget could not be generated at the prescribed temperature of 7 to 8 degrees C at 110 ampere for S235, 957 degrees C at 98 ampere for DP600, and 636 degrees C at 80 ampere for SS316, according to the data in the table. Because the melting point of any steel utilized should be greater than 1000 degrees C, the resist spot welding process would be ineffective unless the current flowing through the machine generated enough heat. However, if a sufficient amount of heat is applied, it is possible that the weld nugget will expand in size as the sheet melts. Aside from temperature, stress and strain have a role in the creation of weld nuggets during the spot welding process. Next, let us look at the simulation from the spot welding process until the tensile. Then we can see at the end the plate was flat. It is because there is presence of tensile in the process. Then, when the metal sheet was subjected to tensile load while the weld nugget was still in contact in a tensile test process simulation, it flapped at the 41st increment. This study reveals that the increment has not converged, indicating that the simulation has reached its maximum stress limit. The figure of the resistance spot welding with and without the user subroutine is presented in the following table. The location where the nugget created is in good condition between the upper and the bottom sheet metals, which make the sheet joint remain intact, causing the sheet metals to flap. Is depicted in the figure with the subroutine. During the spot welding process, those conditions occur due to the force applied, current, and nugget formation. However, when we look at the simulation without the user subroutine, the tensile process cannot be run successfully as the sheet was detached. Thus, the user subroutine is very important in this simulation. Finally, the findings of this study demonstrate the need of having adequate spot welding process parameters to allow a successful observation on finite element analysis simulation, because most of the data used for spot welding is time or temperature dependent. Based on the results obtained by varying the temperature in order to form a fine weld nugget, it is plausible to conclude that as the current increases, so will the temperature, resulting in an increase in the size of the weld nugget. It is vital to have a strong contact conductivity when making weld nuggets. This is due to the heat contact interaction producing heat. Furthermore, the use of a subroutine in this modeling process aids with the attachment of the sheet metal once it reaches 800 degrees Celsius. Above all, after allocating data input to the resistance spot welding process, this simulation simply explores the physical condition of those three sheet metal materials. However, there are still numerous flaws in the study due to a lack of resources to obtain a comprehensive and complete examination of those three sheet metal materials. This is all for my presentation. Thank you, ladies and gentlemen, for lending me your eyes and ears.